Hi there everyone, welcome to the UK. Now I don't know if anyone, probably a lot of people have heard, this morning I got stuck in a lift which was oscillating up and down, just kept going up and down for about 5 minutes. And now I've got to start talking about oscillations. And it's really the last thing I want to do is talk about oscillations. But we'll see how it goes. Hopefully I won't have a panic attack while we're doing this. Anyway, what I'm going to try and do today is sort of explain Fourier analysis. Now I know Fourier analysis has this sort of mystique about it, as if it's something really complicated and that it's hard to understand. But I'm going to try and see if we can make it in a simple way, just by using simple maths. And hopefully by the end of it you'll have a better idea. Right. If we think of sound, we normally think of it as this one single little wiggly line. Now, to that doesn't sort of make that much sense to us. It's a lot better if we can break this down into its component parts, its component sine waves. Now, how do you manage to get a little wiggly line like that, that's got a mix of all these sine waves all together? How do you manage to separate them and sort of with some sort of coherence, you know? Now, if, say, for example, that was our waveform, now you can see, just by looking at that, that's two sine waves. You can see the low frequency sine wave, you can see what level that low frequency sine wave is, and you can see it's a high frequency sine wave, and see that's a different level as well. So just by looking at that one thing, it's quite easy. There's you wouldn't need Fourier analysis to break that down. You can do that by common sense. But of course, waveforms aren't that simple. They're never just two simple sines that we can break down visually. So we have to go into something a little bit more complex. And that's Fourier analysis now. Everyone understands that, so, you know, glad you came, it's finished now, we all understand it, we can go. Well, maybe not. Let's try and do some other method of actually analysing what's going on. Right. So basically Fourier analysis is nothing more than just multiplication and averaging. And multiplication on a signal level is well, anyway, let's look at averaging first. Right, so imagine, say that's a standard sine wave. You can tell that there's equal amount of area above the line as there is under the line. So the average of that is going to equal 0. Now any sine wave, the average is going to equal 0. The only sine wave that isn't is a special sine wave, which is a sine wave of 0 hertz, and that is DC. So that would be like one straight line. So averaging, that's quite easy. We just sort of look at the waveform and find out, add the bits that are on top, subtract the bits that are underneath, and we end up with our average. Right? Now multiplication. Now when we come to multiplication, obviously you can multiply numbers. Everyone knows how to do that. I learned that at school. But when you're multiplying a signal, what you're doing is you're multiplying a stream of numbers. Now, you really want to get a way of visualising what happens to this stream of numbers in your head. Right? I'm going to try and... you can see that basically what's happening is that we shrink the signal down as we multiply it by numbers that are smaller than 1. And then if we multiply by a number that's a negative number, the thing flips up. It turns over. Right. Now I'm going to try and give you a real world version of that. So imagine, oops. Right, well here's my signal. It's on a piece of paper. Now if I want to multiply it or make it larger, oops, sorry a minute. Now, this ain't going to stretch. I should have something like a balloon would have done better. But there's another way I can do it. Rather than, if I'm going to multiply by numbers that are less than 1, then if you sort of look at it straight on, then that's the equivalent of multiplying it by 1. But if you used to look at it at an angle, then that's, you know, what you're seeing now has been multiplied by, say, 0.5. If you look at it edgeways on, you see nothing. That's multiplying by 0. If we carry on, you're now multiplying by a negative number. So the waveform has in effect turned upside down. So we can use the angle that you're viewing things at to actually equal the multiplication. That would be -1, +1, multiplied by 0.5, right? So we don't need to stretch it, we can just change the angle. Now the thing about Fourier analysis, we don't want to multiply it by a single number, we've got to multiply it by a sine wave. Just one moment. Now, in multiplying a waveform by a sine wave is a little bit more difficult to visualize in your mind what's going to happen. But what we can do is sine waves sort of come natural with helix, like things like a spiral staircase that will actually produce a sine wave, right? So what if we use this angle idea? So we're going to multiply by moving the angle up and down, but if we change the angle sort of in some sort of a dynamic way, so we start with, say, our signal, and we start multiplying it, but we multiply it by a sine wave. We can actually do a twisting action, which would be the equivalent of multiplying it by a sine wave. Now, let's try and do a real-world visualization of that. So what I'm going to do is I'm going to use my two glamorous assistants here. Thank you. I was going to get them to wear a leotard, but they weren't too keen on the idea. Just move that out of the way. Right, so here we have, if you can grab that and clip that to yourself. Right, so, yes. Okay. Yeah. Now you're going to start off by holding it that way up. All right, now if you go apart, it's a bit of a tug of war going on here. All right, tug of love, yeah. Now there, all right, is a sine wave. Now you can't actually see the end because we're behind. Actually, let's bring you in front, Marinos. Then we should be able to see it. Okay. You're not going to fall off the end. No, you better go back a bit. Yeah. Okay. Yeah, a bit tighter. Don't use your hands for the tightness. Use. Okay. That's right. Use the strap. Just hold the hands. Just hold it upright. Okay. So basically, here we've got a sine wave. You can see we're starting high. If we average that out, or by the time we got there, we're already averaged out to nothing. So we come along. Here again, we've averaged out. Oh, here we've averaged out to nothing. So all the way along, we look at the waveform. The average of that is just nothing. Right? Now what happens when we start to twist it, in other words, we're going to multiply this sine wave by another sine wave. So if you do a 180-degree turn, right, now if you can probably see it, I can't. Now what you've got to do is you've got to start looking here. Have you covered that? Oh no. You're all right there. You're good, it's just the chair. Right. Right, so just need you to pull a little bit tighter. That way, right? Okay, and you can see what's actually happening now is that we're still averaging out to 0, right? If you look at the whole waveform, you're averaging out to 0. So if you can do one more twist in this direction, all right? Just still look at the above and below. Still got an average of 0. Oh, has he come out? Okay. Yeah. Well, you can actually let go. It's not necessary. All right. One more twist. Now we're getting close. Now all of a sudden, very soon, when we get to the next twist. Right, you're going to see, one more, that's it. You're going to see, can you see everything's going upwards now? Nothing's going down. The average of this is a number that's bigger than 0. Now it just so happens that at this frequency, I mean there's two twists in effect, two complete twists, and the sine wave is actually, there's 2 cycles for the whole length. Now when that happens, that means at that moment in time, we've now got a positive average, right? You do just one more half twist, one more. Now you can see it started to go, the average has now disappeared again. We no longer got this offset, right? So that's basically, now you've got that in your mind, we're going to go and have a look at a more detailed version on using Kyma. So you can now untwist and we'll put the fella back. Well, it lasted because this was actually going to perish, right? So let's bang him away. Okay. That's how Rubber Johnny has been used by both Marinos
I didn't mean that.
Okay.
We were okay for a while.
Thank you very much, gentlemen. Keep your strap on, yes. Right, so now you've got the idea, hopefully, of what actually happens when you multiply a sine wave by another sine wave of the same frequency. So let's... wrong one, sorry. Here we go. Right, so what we're going to do is I'm now going to use Kyma to actually try and demonstrate this, but we can, I mean, with there we had a single sine wave. What happens when we have a quantity of sine waves? Right. Okay. Right, so this is in effect, this, you see this part here, that is, I mean, Gustav is sort of standing over here. No, Gustav's standing over here and Marinos is standing over here. Now, if I just put in a sine wave, for example, we'll turn that one on. So that's the sine wave that was actually drawn on the piece of rubber. And now I'm going to start to twist that. So you see the twisting action, same thing. All right? But when I gradually go up in frequency, and basically here I've got something that's measuring the average. So all the time, the average is nothing. Until we get to a point where the actual twist frequency, hold on, no, I have to type it in. Right, now the twist frequency actually equals the frequency that we're analysing. We can see, can you see the average over here has gone to 0.4. The original over there was actually 0.8. So the average is obviously going to be the half, because obviously if we chop these bits off and fill them in there, that's going to actually, this line here will be the average. When we were back at DC, I'm now going to put DC in and go back to untwisting it. With DC, we had 0.5, but the average was 0.5. So DC is the exception, right? With DC, now the other thing about DC is when we start twisting it, the DC becomes nothing as well. All right? Now, what if, say, for example, we have this 250 here, but we mix in another 800 hertz with the signal. So I'm going to put the twist frequency at 250. Now it's got the 0.4. If I take the 800 hertz out, still 0.4. So mixing it together, because the 800 hertz is still averaging out at 0, we're adding 0 to our 0.4, and it's always 0.4. Right? I could add 3,000 hertz as well. Whatever we add, we can add all these other frequencies, and it doesn't matter. It's only this frequency that actually changes the average at the end. So here, I can add these frequencies in, and they're all averaging out to nothing. The only frequency in this situation that's going to actually give us an average that's not 0 is that one. Now let's say I make let's say I make the twist frequency something else. We'll make the twist frequency, say, we'll go up to the 800. Well, close to 800, so let's see what happens here. Well, close to 800, you can see it's starting to drift. The average is starting to come up. The actual 800 level at the moment is 0.5. If I make it exactly 800, now we're 0.25, which is the half of the 0.5. Same thing, now I can add 250 hertz in. It doesn't make a single difference, it doesn't make any difference to the average. So what we're doing is we're now seeing, basically we've now got a frequency content detector, even if they're all mixed together. If there's loads of sine waves, and by having this twist at 800 hertz, we're going to find out how much energy there is in 800 hertz only. Sorry. Now, there's one other thing here, and I've been sort of cheating a bit. This looks like it, we're finished. We've now got We've now got a sort of Fourier analysis. It's all sorted. That's all you've got to do. Multiply it by a sine wave, and you've got the answer. Let's just go back to the 250 again. Right, so we put the 250 down. Now, of course, we've got that wonderful number, the 0.8 there, 0.4. Every example I've shown you so far, they all start in the same place. The twist and the actual sine wave. What if it didn't start? What if it was actually the 250 was in a different phase? Let's say I'm now going to move it round. Oops, move it round to 180 degrees out. Right, now the average has become -4. Right. What if I changed the phase to say 90 degrees? Now that's averaged out to nothing as well. So what we've now got is we've got a situation where we can find out the value of a frequency if we're lucky. If it's in the right phase, we'll find it. But if it's in the wrong phase, then we won't find it at all. You know. So there must be a way that we can do this to actually overcome this getting rid of the luck. Well, what we could do is we could actually analyse, change the phase of the actual analysis, the actual twister. So let's say, for example, I'm out by 90 here. Let's say I change the phase of the twister. So if the twisting phase was 90 degrees, then we got back to that value again. Now, does that mean I've got to make a twister for every single possible phase that we might have in the original signal? Well, actually, no, we only need 2. If I was to... I'm going to put that one back there. In fact, I'll open up a new one here. We're now going to do 2 of them. And what we're going to do is we're going to have one twister. One twister is the 0 phase, and the second twister is going to be 90 degrees out of phase. So let's see what happens here. Back to... We'll put our 250 back in it. Right, so one of them, the first twister, is at 0.4. The other one has averaged out to nothing. All right. So what if I change the phase of the actual the audio signal? All right, now what you can see at this point, this one's 0.4 and the other one's nothing. Say I put it at 45 degrees, so I'll try and trick it and put it halfway between the two. Well, they've now both got something, but they're not quite. They're not. Neither of them are actually telling us what the value of the signal is. By the way, the other frequencies, it doesn't matter what phase they're in, they're just going to have no effect on this detection, right? The only problem we've got a phase with, and it's the only time we've got a phase problem, is the actual frequency we're trying to detect. But now we've got the 2. What I'm going to do is I'm going to actually let it drift. I'm going to let the original signal's phase drift. So let's just watch it drift. Now, as you see, just look at these 2 averages. And you can see one going up and one going down and there. Now, I don't know if anyone can notice a pattern of what those averages are doing. They're actually making another sine wave and another cos wave. So what if we took those 2 averages and we actually put them into an XY plot? Let's see what happens when we do that. So we have the next one. Alright, so we're putting our 250, putting our 250 in here. Alright, so this is now the first phase, which is the 0 phase, we're calling the real. And that's going to move this up and down. And then we've got the imaginary, and that's going to move it left and right. So now I'm going to let that drift happen again. And we can see what happens. Sorry, I've just not been keeping this up to date. All right, so I'll let you have a quick read of that. All right. And then this is where this is what we mean by real and imaginary. We actually multiply by a sine wave, and then we multiply it by another sine wave that's 90 degrees out of phase. And then with those 2 values, we can then work out how loud it is. So I don't know if you notice that this is going around in a circle, and the distance from the centre is always remaining the same. So I could calculate that distance from the centre using a little bit of Pythagoras, because basically you square, you think of it as a triangle, and then use the square of the hypotenuse is equal to the sum of the square of the two adjacent sides. So the hypotenuse would be magnitude, and then the real and the imaginary would be the two adjacent sides. So what I'm going to do is I'm now going to take those values and I'm actually going to square them, and we'll see what result we get then. Alright, so once again, 250. I'll just let it drift so that you can see. Now the magnitude is flickering about, but the magnitude is now 0.4, which is exactly half, 0.4 here, which is exactly half of the 0.8 there. If I change the value of the actual input signal, let's say, and so the magnitude changes as well. So that is a representation of that magnitude. It doesn't matter if other frequencies come in or anything, they just don't get in the way, they're just not involved. The only thing is that one particular magnitude. If I change the twist frequency, I mean I'll put the 800 in there, and we'll change our twist frequency now to 800. Now I've still got the same thing, it's drifting around in a circle, but now that's nothing to do with the 250. It's only the 800 that's actually changing the magnitude.
Right.
So, okay, so I think we've now cracked sort of the idea of detecting any of the frequencies we want to detect. We just multiply it by a sine wave and multiply it by a cos wave, a little bit of funky maths, and then we can actually find out how loud each signal is, and we can even find out which phase it's in just by doing a bit of trigonometry. Or, as I say, you can measure it. All right, now the thing is, how many of them do we need? Because that's obviously, we can use that to pick out one frequency. We're going to want to pick out lots of frequencies. We could sort of randomly choose frequencies and things, but there is a set of frequencies that virtually everyone uses, because it means that you can actually get backwards. You can actually, if you do this amount of frequencies, you'll get back to your original, you get your original signal back, right? And this is where the frequencies are based on, you pick a frequency and then you do 0 times that frequency, 1, 2, 3, 4, 5, all the way up to half sample rate. And if you make a slice that is the width of the period of the very first frequency, your actual analysis frequency, then by synthesizing the sine waves that you get, or synthesizing what you get back, you will actually end up with exactly the original signal. Now that doesn't matter, even you could have sort of hundreds of sine waves in there, you only need those frequencies. Like say for example, our frequency was 1 kilohertz, and we was using 48k was our sample rate, then we'd need to get to 24k, so we'd only need 24 analyses, and that'll be enough to turn it into the frequency domain, and then we'll be able to use that, synthesize it, and get back to the original signal. Right. Now FFT is just this method that someone came up with, where they can make the maths much quicker. It takes less computing power because because there's so many of these that you want to analyze. They've got funky ways where you don't have to analyze every single frequency separately. It can do it all at the same time, and it takes a lot less computational power. But to do that, you normally have to have your base frequency has to be related to the sample rate. Otherwise, you don't get the efficiency that you need for FFT. Now that's why I call that the safety net, because if you choose those particular frequencies, that means that you've got a get back path. Right. Now the thing about the safety net, about those series, is that I keep saying we can get the original signal back. That's only on one condition, that we don't do anything in the middle. Right. Now, of course, what's the point of doing this analysis? Right. We've got all these wonderful sine waves, And then we say, okay, well, we've got our original signal back. What's the point of that? It's no good at all. We want to do things in the middle. Now, it's when we do things in the middle that odd things happen. Right? Let's just sort of think of everything we'd want to do in the middle, like time stretching or pitch shifting, format manipulation, morphing, in component isolation, that sort of thing. We rely on the phase of these things changing. If you want to change the frequency of something, the phase relationship can't remain the same because, by virtue of the fact that we're actually going to take the pitch up, you can't keep the phase the same, because if you keep the phase the same, you can't change the pitch. It just won't work. Mathematically won't work. So we basically we're going to things in the middle are going to have to change the phase. Right. The good thing is that you can change the phase of all harmonics, and we don't hear it. We're totally oblivious to the phase relationship of harmonics. We just don't hear it. As I don't know if anyone was at the KISS 2012, where we actually had showed these two waveforms, and they were indistinguishable from each other. One was a square wave, and one was a square wave where all the harmonics had been shifted by 90 degrees. But to us, we can hear it. And you could even put sort of really complex sounds with percussive and all that sort of stuff. You put it through the Hilbert transform, which shifts all the phases by 90 degrees, and we cannot tell the difference. So I mean, that's a good thing about it. So that means we can do whatever manipulation we want to do. Right. Now the problem is that if we want to sort of change these phases, then really you want each band or each detector to have just one sine wave in it. Because if we have multiple sine waves, then what's going to happen is we're going to be moving maybe two in the wrong phase. Right? So this is where doing things in the middle actually means that the standard Fourier analysis doesn't work that well. Right? So I'm saying the three main reasons here is windowing errors, right? Signs that border between two bands, so it actually appears in two places, in two bands, and the last one is more than one sine wave in each band. So let's take a look at a little bit more detail. Windowing errors, what I mean by that is, let's say, for example, we've got a frequency that isn't an exact subdivision of our window size. Our window size, don't forget, is the period of the lowest frequency we're analysing. What's going to happen is it's not going to average out to zero anymore. You see that little bit of green on there? I mean, the two other halves average to zero, and then you've got a bit that says, well, I'm not zero anymore. And so there's sort of a way we can improve on this, is that rather than having a square window with sharp edges, all right, so by the way, when I mean windowing, I mean we're going to take a slab and then take the next window and take the next window, do a bit each time, and then we'll add them all together or put them back in the same place at the end. But what we can do is we can actually fade it in and fade it out. But we have to make it twice as wide first, so so they'll overlap with the next window that's coming along. So I don't know if you can see on there that sort of shape that's a hand shape. That's actually a sine wave that's sort of offset a bit. So it's not quite. It's not a standard sine wave because it's not swinging around zero. But that's just basically we fade it in and fade it out, and the next one will come along and that will fade in and fade out. So we can see basically we can have different window shapes, but the hand is quite a common one. Just going to have a look at these are windowing functions. So what we're saying here, first one is a square window, and you can see that what's going to happen if you look at the expanded view, you'll see that there's little like side lobes, but between the side lobes, those little gaps, that's where it does balance out perfectly. All right, so it means that you're going to balance out if it fits in a window perfectly, and that's where those, I don't know how clear it is on there, but you can see below where it's got the bins. They're calling them bins. It's what I've been calling bands. Right? Where it matches, it perfectly cancels out, and you get those negatives. Where it doesn't match is where you get these side lobes. Now, if we do look at the hand window, which is the one in the middle, right? Then we've still got the side lobes, but the side lobes have been brought down vastly in comparison to the frequency we're trying to get. So that will improve things quite a lot. There's actually another one here, is an exponential window. Now, the exponential window doesn't have any side lobes. It's actually quite a smooth decay either side. But of course, the actual separation isn't that good. So, and the other thing about the exponential window is you can't overlap it. With the hand windows, we can overlap it, and it always averages out to 1. But if you've got something that's pointed at that, you'd have to have one on every single sample to try and sort of get an even flow across your signal. So an exponential window is not really that good, even though it's got some nice features to it. Well, that's the windowing problem. The second problem was if we have sine waves that are actually in the middle of 2 bands. Now that's not going to be uncommon because when you consider between our first 2 bands is actually 1 octave. So the chances of actually having sine waves falling between 2 bands, or in fact there's the 2 problems now. I'm going to show you the next one. This is where 2 sine waves fall in the same band. Or if it's noise, it's going to fall in lots of bands, you know. So basically, that's the reverse. That's the 2 problems, but it's sort of the same idea. In other words, too many sine waves for the bands, or too many bands for the sine waves. They both give us a problem. Sorry. Okay. Now, of course, these problems, we can't, the windowing isn't going to help with this. That's just a function, right? Now, there's sort of, these are things that give you artifacts. The fact that you're trying to manipulate 1 sine wave, but of course you're manipulating a quantity of sine wave. You can't manipulate them the way you want, especially with phase shifting and that type of thing. Now, as I say, one other way of doing it is if we actually make a lower frequency, that's our analysis frequency, that gives a lot more bands. But because it's a lower frequency, it means the period's going to be longer, and if the period's going to be longer, the window size is going to be longer. And if the window size is going to be longer, then we have the problem that these problems here, where we have a poor transient and small sine waves will actually get lost. They won't even be registered within a wide window. So it's not an exacting science. This is not the sort of thing that you can say one thing is going to cure all. It just can't be done, you know. Anyway, there are sort of funky tricks that people have used, you know, to try and get around this problem. So bear in mind. As I say, you'll notice that Kyma uses, in the harmonic analysis I'm talking about, not the other one. In the harmonic analysis, you'll notice that Kyma makes sure that there's only 1 sine wave in each band. But of course, that has to be a monophonic signal. You can't do that with a polyphonic signal. And once you've done that, and you're using a sum of sines to actually reconstruct the sound, then things become a lot easier, and you can actually end up with sounds that are quite clean. Still have problems with noise portions. You know, let's say we've got speech and there's some noise parts that can still give problems. But in general, it's a pretty good approach, and I don't know how Kyma manages to get these signals that are moving up and down, but yet maintain this relationship between 1 sine and 1 band. It's a trick that I think she's keeping to herself. And I don't blame her. You know. Well, I've been thinking about, let's think of a different approach altogether. All right. This is me thinking about, let's go right over the top. All right. Let's not have the limit of this Fourier series. All right. Let's say instead we had loads and loads and loads of frequency bands. All right. In fact, you know, whereas before we saw for the first part there was 1 band per octave, well, I'm actually going to have 14 bands per semitone. That's quite sufficiently over the top. You know, let's say we had that, And then let's say, rather than the windows overlapping, let's say we had the windows overlapped ridiculous amounts. Every single sample had its own window, right? Huge amounts, right? Now, here as is an example. This would be what our frequency would be. We wouldn't make the frequency bands any narrower. We're not going to try and increase the size of the window. We don't want the smearing that we got, but we just let them overlap. We have lots of bands and just let them overlap. So we will still have one sine wave will appear in many bands, all right? But at least all the sine waves will appear in many bands. We know we can cope with it then. We know what to expect. We know what we're looking for. Similarly here, this is the same thing with the windows. You know, there's basically sample number 10 and sample number 20. You can see that there's going to be, those windows are going to overlap. So it's going to be really smeared, right? It's just an idea. Let's say we just do things over the top, right? Now, how would this look if we did something like this, right? Well, we've got to represent it. We've got to see what we've done, right? Let's say. So what we're going to do is we're going to make each pixel on the screen, right, become the result of one of these little analyses. Right? We'll have the real and the imaginary, right? But so each pixel on the screen will be a sample, right? But each sample is going to have a complete Fourier analysis for that one sample. And we're going to have too many frequencies. We're just going to fill it up with so many frequencies, it's just unheard of. But then right next to it, the next pixel along, is actually going to be the next sample. We're going to do the same thing. So let's see what this sort of thing would look like. So we're going to this is sort of like an artist impression of what it would look like. Now you see all the pixels there. If you look at the center line, then that's obviously going to be where the frequency that we're looking for is in line with that particular frequency. But as we move up in frequency, it's still going to bleed through, but it's going to become sort of less noticeable. I mean, the high and the low are not going to be so easy to. It's basically, it's going to be fuzzy. It's going to be a fuzzy picture, right? But imagine that, I think that looks like a little pearl, right? Each cycle in our signal would have one of them, but each harmonic cycle would have one of them as well. So we're just sort of zooming into one little area of what it would look like, okay? Well, is this pearl analysis? Well, it's just a concept, all right? Problem is, I don't know of anyone who's sort of doing this on the market. Right. Obviously, it would require lots and lots of processing to do all this huge amounts of analysis. In fact, well, as I say here, only a fool would start off with a 1 meg sound file, and it was going to produce at least 1 gig of data. It's so over the top. Only an idiot would do it. So I doubt if we'll see anyone do it on the market. Well. So what I'm going to do, I'm just going to try and move this over and show you. I spent 2 years trying to program this concept and turn it into something real. So bear with me a moment. Oops. So, okay. Right. This is my pearl analysis. Can you see that? Yeah, we're all on the screen. All right. So what I'll do is let's just say I'm going to start off with a. Just going to generate a square wave. All right. So we're starting the analysis. This is, you can see how long it's taking to do this. So at the bottom, that's the square wave that I've generated. All right. And up here is the sheet. All right. Now you've got to realize each single pixel that you're seeing on the screen there is one of those little analyses. All right. Okay. Now, not only that, I mean, the fact is I can't fit it all on the screen. So if you look carefully, I'm now going to move this from left to right. Right. I'm still not getting there. Still. Right. You'll notice at the end the actual pearls get distorted. That's because it's the end of the square wave. The end of the square wave stops and you get a click, and that is actually a representation of the click smearing itself over the frequencies. Right, so we've got loads and loads of data. Now considering that all the, sorry, scroll. Is it working? Oh no, I've become unclipped. Just put that back on. So just considering all of that, I don't know if we can hear this. I'm just going to play you the square wave. That's how much time that represents. Right? So you've got an idea of just how over the top this is. Now, okay, so we've got all this stuff. What are we going to do with it? Right? How can we actually make any use out of this? Right? Well, what we're interested in is we're interested in the peaks. We're only interested in the peaks of each of these pearls. So if I could go through and by sort of measuring the sort of either side of this pearl, measuring if it's higher than this neighbouring pixel, both north, south, and east, west, right? And I'll mark them. I'll mark. So what I'm going to do is I'm going to do some dot detection, right? And we just go and find all those peaks. So you see little red dots there. Now that's actually it's now going to found all those little peaks. Right. Okay, so we've now analysed. Let's try and do it with some real signals. How are we going for time, by the way?
You've got 13 minutes. 13,
okay. Let's do it with some real signals. I'm just going to turn this one off. Let's have a look. Just want to check on here. This is actually Andrea Young's voice. Now, of course, because it takes... So because it takes so long to analyse, I just want to sort of get one little section of it. So we just go in and... So you see each of these squares here, they represent that 8,000 samples that we just heard with the square wave. So that gives you the duration of that bit. So I'm obviously, that's not going to be enough. I'm going to have to do a few of these slices and join them together to try and make something of it. Okay, so we do that. Let's say we don't want to be too long. I just do 3 slices. So that's how much. So I'm not going to analyse that. I get rid of the dots to start with. Okay, so you see how long it's taking. Okay, now the problem is, of course, that's where it's coming in. I'll just show you. I'm going to have to zoom out, right? Now, the other thing is once I zoom out, then we stop seeing all the pixels. So I can also show it as magnitude instead. So if I click on magnitude, and what that's doing the real and the imaginary. Now we're actually seeing how much level there is at various points. So that's what we're getting in magnitude there. But I've got to, first of all, I'll zoom the height so we can see all the frequencies at the same time. So that's where's the point on here? 0.5. And we're going to have to zoom this out a lot. Let's go say 0.05. I've zoomed it out quite a bit. Okay. Right, so that's actually now 3 slices. Right. We'll just check on the source. Now what I can do, if I go back to those dots, in fact, show the dots. So it's picked up all the dots now. I can click on one of these dots. and construct a string. Had a little bit of a problem there at the break. Now, what I'm going to do is I'm going to try and resynthesize that string. So in other words, each of those dots is going to make like granular synthesis is going to make one, basically it's two cycles of a sine wave, but inside a hand window. So let's just see if we can hear that. Oh, that doesn't sound very, oh hang on, I haven't rendered it yet. Render the string. Just to let you see, this is, oh, they look pretty similar, but okay. So that's the first harmonic, and I can click on here, and then we'll render that. Click on here. Right. Oh, okay. Right, so you can see that's basically, well, it's going to take a bit of time, but you can see we're starting to get something like the original signal. Well, this was the first time I actually got sound out of this was 3 weeks ago. Right? And I started doing this, I say, okay, I'm going to have to do something to help me pick out all these. I then said to myself, what if, I've got all these dots here, what if I say, hang on, let's, all this I think I've explained most of this to you. Right, hang on. What if I just did all the dots? Right. What I'll do is, and I said, well, what I'll do is I'll do something a little bit more complex than a single ooh, because that's quite easy. So I'm going to have to reboot this because I probably run out of RAM in my computer. So I'm just going to have to quit the program and start it up again. Okay, so what I'll do is I'll get a signal that's got a lot more harmonies in it. I'll make sure we've got a bit of sibilance. Okay.
The day breaks. Yep.
So let's try about here. Hang on.
She wakes up. She takes her time and doesn't feel she has to hurry. I will say.
Right. Now here we've got a bit of sibilance. I will say, and we'll zoom into there. Let's try there. We'll try, say, about 5 slices. So just play that section. So we've got harmony, we've got sibilance, we've got this nobody sort of thing going on there. So let's actually analyse that. Right, let's just bring down the contrast a little. Right, so that's the input signal there. Right, this is what we've got as our analysis. I just take the dots out of the way so you can see the raw analysis. Right, so you can see I'll play you what the original is. So you see the S at the beginning, and then these are all the various harmonies and the harmonics of the harmonies. I just zoom in a little bit. Yes. So okay, so I'll show all the dots, and what we're going to do is we're going to just do all of them. We just, all the dots, if it finds a dot, it renders it at the appropriate volume. Now, of course, I haven't really done any work on this, and it's going to need a lot of work to actually get it to. But what hopefully, well, hang on, that's the input signal. I'll render all the dots now, and above it will be the signal that is actually rendered. It takes a bit of time. Right. Now you can see it's not quite the same. It's got certain similarities, but if I want to see if you can sort of hear any of that original at all in there. I mean, obviously it's going to be a mush. It's not going to be much. Right. So anyway, so what I'll do is I'll play the original, and then I'll immediately play the rendered one, so that you can do a sort of a comparison and see if you can you can actually hear any of the original in it. So here's the original. Here's the... Now, I don't know if you're surprised, but my jaw hit the bottom of the floor when I heard it. I'm going to play it a few more times because I couldn't believe it, right? Can you hear the difference? It shouldn't do that. It's gone through too much crap in the middle, right? It shouldn't possibly... Now, so I thought, well, okay, just make sure I'm not actually hearing the same thing. Right? Let's do something in the middle, right? So what I'm going to do is I'm going to make all these sine waves, I'm actually going to squash them up. So it's going to be like a formant shifter, but it'll be a polyphonic formant shifter. It won't be a... normally with a formant shifter, you've got to find the fundamental first. Right, so we're going to put in, say, 1.5 here. So I don't know of polyphonic formant shifters. I think that's a... I'm going to see what happens. Just bring it up. You can hear they've all got that sort of same... Let's go and do it over the top. It's going to have a real terrible form of, let's go up to three times. 300, no, 3. 300 just wouldn't hear anything, I don't think. Okay, all right, so let's bring that. I've run out of volume here, actually. You use a little bit more. Right. Now, the thing is, it's not perfect because I let Gustav have a play with it, and he put some sounds in it, and he found that things that had a lot of percussive, very electronic percussive stuff, you could hear there was a bit of smearing. So there's a lot of work has got to be done on this, right? But I think, and also trying to sort of separate harmonics. It's well, let's put it this way. It was only 3 weeks ago I got it to get it to make any noise. All right. Since that time I've been preparing for this, so I haven't touched it at all. So I've got to go back to it and start finding out just how good or how bad it is. I mean, it might be that I've conned myself and that it will only work if you do nothing in the middle or very little in the middle. But I think it's let's put it this way. It's looking sort of promising, and actually, I think I've managed to do. I think I've actually managed to get into the hour that I thought I wasn't going to get into. So if you want to have questions, we could go.
A couple of minutes left.
Okay.
Do you want to take some questions?
Yeah, we'll just take it for a couple of minutes.
First of all, can I say thank you?
Right. Okay.